Okay, all right. Hello, I'm David Xu from the National University of Singapore. I'm the moderator for today's panel on model-based and data-driven robotics. Our panel today is slightly different in topic compared to some of the earlier ones in the series. Our earlier talks and the seminars and panels cover some of the most exciting subfields of robotics. Today we have only one topic, one question, model-based and data-driven robotics. But arguably, that's probably one of the most important questions facing all of robotics today. I'm so excited to have four distinguished panelists joining us today. Aude Billard from EPFL, Sergey Levine from UC Berkeley, Russ Tedrake from MIT, as well as Toyota Research Institute, and Michael Wang from Hong Kong University of Science and Technology. I don't think that any one of them need a long-winded introduction from me. You are here to hear their perspectives and insights. All of them have made immense contributions to robotics. All I would add is that together, four of them span 3 continents for different time zones, and more importantly, they represent distinct intellectual traditions and interests spanning all the way going from model-based to data-driven robotics. We want to make our panel as lively and interactive as possible. So in addition to our 4 panelists, we invited 9 guests to join together on screen. So these are Pan Cai, who is a postdoc from National University of Singapore. Pan, thank you for joining us and staying up late at night. Shamik Ganguly, a PhD student from Stanford. Shamik, thank you for getting up so early. And Leslie Kybling is a professor from MIT. Leslie has a lot to say about this topic. I'm pretty sure of that. Thank you so much for joining us, Leslie. And Alina Kolos is a PhD student from Max Planck Institute. And Hannah Kuniwadi is a faculty member from the Australian National University. Gilbo Lee is a PhD student from University of Washington. Yonghyun Lee is a PhD student from Seoul National University. Aoran Song, a PhD student from Hong Kong University of Science and Technology. And Mark Toussaint, professor from Technical University of Berlin. Thank you, Mark, for joining us. And to all of you who have to get up very early in the morning and stay very late in the night, thank you all of you for joining us. And I hope that the panel will be interesting to you. Now, a quick outline. As I mentioned, to make our event panel as interactive as possible, we'll interleave the panelist presentations with question breaks, short and long. And at the end of that will be an extended question and answer period. So our guests will share the screen and they will pose their questions directly to the panelists and share their own views and comments. And for the rest of you who are connected through the internet, please send your questions to Slido, and I'll monitor Slido, and I'll collate the questions and pose the questions to the panelists on your behalf. Right, so that's a plan. Now to get started, I want to say a couple of things. To start, I would say that a robot system, after all, at a very abstract level, just takes as input sensor data and tries to compute the action for the robot to execute. So after all, it is a mapping from sensor data to actions. Now the rest is just how to construct this mapping. So there's the model-based approach, and there's the more recent data-driven approach. This is my caricature view of the model-based approach. F equal to MA is probably one of the most famous models, and it probably sits somewhere in most of the robotic systems. These laws of physics and other laws of nature form the foundations of many robotic systems, and actually, in fact, most of the engineering systems as well. They include some of the most famous robot systems everywhere, everything from Shaky to Stanley to Mars rover and so on and so forth. So they have achieved a tremendous success over the last half a century, and much longer than that in terms of engineering systems. Now, the data-driven approach to robotics is much more recent. However, their success is astounding. So look at this example from OpenAI on in-hand dexterous manipulation. and also that the data-driven approach is widely embraced in the autonomous driving industry. Now, some of these tasks, the model-based approach faces great difficulty, even with decades of research. At the same time, if we look at this in-hand dexterous manipulation example using the data-driven approach, so if we, as far as I know, if we shorten the index finger by a couple of inches, or maybe we change that cube into a pencil, whatever learned skill demonstrated here probably becomes very unuseful, and we probably will have to learn from the scratch. That is hardly generalizable learning. Now the question would be then, what lies ahead between model-based and the data-driven approach to robotics? Well, maybe the train has already departed the era of model-based approach despite its past success. All future is to be driven by data. Or maybe that both of them will coexist, but live in parallel worlds and divided by a chasm. I hope that is more interesting than that. That is the topic of our discussion today. Before we dive, let me just add a couple more points. Even though it is true that the robot system mostly just maps sensory data to actions, but this could be a very complex mapping. At the bottom, we think about things like position, force, torque, contacts, and so on and so forth. We put together these basic elements and to form primitive skills, maybe that to pick up an object, or maybe shake hands with a human. And putting together these primitive skills, maybe after a few layers, we get to the really top, more complex tasks, as well as try to understand human intentions. For example, how about to get a robot to help the human to do cooking, right? So when we pose the question of model and data, we must keep in mind that we are posing at all these different levels of complexity. Finally, let me say this one last caveat. This word model is heavily overloaded and sometimes very confusing, right? To some people, the model means a very compact, general, and analytic formula like F equal to MA. That's what they mean by model. To other people, a very powerful functional approximator such as neural network is just a model as well. I'm not sure that it's possible to define this precisely mathematically, but I want to just bring this up to make sure that we are all aware of this potential confusion. And I will also ask the panelists to possibly clarify their usage within the context if possible. That's all. Now let me pass on the screen to our first panelist, Aude.
Hello, everyone. Thank you very much, David, for this incredible introduction. Thank you also to Osama for organizing this meeting. I very much look forward to the actual panel and to the discussion, so I really don't want to spend too much time on my presentation. I will share my screen now. Okay, so yeah, I'd like to get started with the key question, which is, should we have physics-based model or should we have data-driven learning? And I think it's not a versus, it's not an either or, it's really we want to have both and we want to combine them. And I'd like to show several examples of why. But why do we want to do that? Because we want to use physics-based model for all what we know how to model. When we have a model, then we should definitely use it. And then we should obviously use data-driven learning for what we do not have prior information or for which we don't have any model. So I'd like to start with the very first example that everybody is very familiar with, is just grasping. Imagine you want to have a robot and compute the grasping point and compute a feasible grasp on an object. Then the first question we have to ask ourselves is, do we have any physics-based model? What do we know? What can we give to the robot to start with? And there is really a lot that we have at our disposal nowadays. We know how to compute stability. We have different criteria. One of them is force closure. We have the kinematic for most of our robots, so we can know what is kinematically feasible. We can also compute collision with the actual object or with all the fingers. So what do we not have? And I think what we don't have are really the real physical properties, the physical coefficient, which is always very difficult to approximate and it's never really constant on any object, the actual mass and especially the mass distribution. I'll come back to that. So if we just look at what we have, the physics-based model for grasping, what we can do is that, at least in simulation, we can simulate and determine for a fixed number of grasping points on a given object for which we have the shape here. I just show a cylinder. We can minimize, for instance, minimize the torque, minimize different objective function, and then it ends up to be a non-convex optimization. And we can find different solution, not necessarily global, but we can find different solution. And so typically we can find, in this example, 1,000 different grasps, and some of them, if we look at them closely, they're very similar to human grasp. So basically, if we just go model-based, kinematic-based, we already have very, very good solution in simulation, which we can also implement on real robot, and I'll show you here a couple of examples. So yeah, these are simple examples. We're still model-based, we still computed all these grasps in simulation, and you see that you already have very good results. You even have generalization. We learned that from a cylinder, but we can still grasp a variety of objects. So it will look like this is very good and we can just be model-based. But in truth, the optimization was very slow, very demanding. And each time we were basically solving a very nonlinear problem, and it will take a few seconds to run. And the worst is that sometimes it will lead to infeasible solution, which you really want to avoid. So we thought, well, maybe, and this is just a bunch of these different 1,000 grasps that we found. What we could do is, as opposed to run each time the optimization, it's a bit like a human each time trying to plan and replan the plan to go to the same place. Rather than doing that, what we can do is take all this data, and then now let's learn once for all a closed form distribution of what we will call the feasible space of posture, typically on this cylinder. That will mean that you build a representation, which here I show a slice. It will be probabilistic representation. So it's typical machine learning. You can use whatever probabilistic method you want for doing that. Here in this case, it was a mixture of ghost function. And so this probabilistic representation is in fact a very high dimensional representation of the feasible space of posture. And so you have a manifold of feasible grasp. And the important thing also is that you have everything that is outside this manifold is practically infeasible. So you should not even try to go there. And once you have this representation, which is in closed form, it's a function. You can derive it and you can compute the gradient. And then you can simply do a line search. So you can have your robot start from any possible configuration and then go to the closest feasible grasp. So I'm not going to show any video in the interest of time, but this is one example where you merge what you know how to do with model-based. But because it's too slow and because also sometimes you get infeasible solution, then you combine this with machine learning and then you store a complete solution once for all. So it resembles very much the way that humans learn. Huh? We plan the first time, and then once we have done the same actions several times, then we learn them and we have some automatism going on. But I said in the introduction that there is another reason for using data-driven approach. One thing that we did not have in this model-based approach was typically information about the friction coefficient. And frankly, it's very difficult to have the real friction coefficient. So what will happen is that if we give to the robot a glass which is very slippery like this one, and we haven't put exactly the right amount of torque, then it will slip from the finger, or even if we move it slightly. So how can we learn this? And I think their learning is really very useful, especially if we can adapt very rapidly. The way that we approach it was to learn by getting the robot some data from demonstration. So here the robot can get this data from observing different placement of the finger. And so we can go again back to physics and say, well, if we hold the object in our hand, we need to hold it stably. So we know how to represent that physically. We can have an impedance model at the level of the object, but what we don't know are the impedance parameter, the stiffness. We don't know the mass and the mass distribution, but we know that if the object is stable, then obviously the center of mass is at the center of the fingertip. And so from that, we can combine a model-based approach with data-driven to infer the physical parameter for this particular object that we did not know. So we can infer some of the implicit friction coefficient through the impedance which is needed to avoid that the object slips and the mass distribution. Further, and we added a lot of other data to learn, typically to adapt to different weights, but we see here different adaptations. So we have the first adaptation once we have such a model to disturbances. The disturbance can also be, as we see here, typically increasing the amount of of content in both of the object. And interestingly also is that we can have what is called regrasping. We can have the robot quickly recompute a new grasp because we've embedded that into a closed form solution. So you see, this is an example where you really combine model-based technique and also learning for getting the parameters that you're missing and getting the closed form solution. But still you rely on impedance control and traditional force closure approach to grasping. Here I'd like to talk about another example, which is fairly similar. Let's say that you want a robot to travel to a path, to do a certain path, but in contact with the object. So certainly what we have at our disposal is so to plan and generate stable trajectory, stable that stabilize at a certain point. This can be done in many different techniques. And so this is to a large extent a problem for which we have many solutions in physics-based model. But what we don't have usually is to know which impedance to apply. We know that we can apply impedance control, but we don't necessarily know which impedance we have to apply, and especially when and where. So an example would be to strike a match. It's obvious if anybody has tried to strike a match, if you're too compliant, then nothing happens because you're not stiff enough. But if you're too stiff, that's what we see here, the match will break. So then what is the right amount between compliant and stiff? And in fact, if you study this model, it's not a matter of fixing one stiffness for the entire path. Actually, the stiffness has to vary, and the way it varies is difficult. So to encapsulate explicitly with a model, there does not exist a very easy way to represent that physically. But it's very easy to actually teach. And this is one example, is just shaking the robot to represent that where you shake the robot, you should lower the compliance. Since the human knows how to do it, it's a very, very easy way to provide the data. And you could provide this also through reinforcement learning or other learning technique. So once you have this, then the robot will change, will be very stiff, and then just the right amount of compliance to strike the match. And we tested that, of course, with different matches to show that there was generalization across matches. Another example, which we really chose on purpose, and some of you probably know it, is to catch a flying object, which is like this one, is tricky because it's half filled with water. And we picked really the half filled with water on purpose because this highlights also this need to represent something that for which we don't have physics-based model. How does the water travel when the object is actually flying? But in order to get this robot to catch the object, we did not do the things totally data-driven because I believe this would be the wrong way. So we did combine physics-based model and then data-driven learning. We had physics-based model for planning and generating stable trajectory to the object. And for that, we have different methods for doing this. And then we use the data-driven learning to learn for which we had really no way to model that, which was typically the dynamics of the flying object, which depends very much on the content that you have of water in the object, which even if you were to measure it, you could not model it explicitly. And finally, and this is really to come back to what David said at the beginning, the most difficult part of robotics nowadays is to model how to handle deformable objects such as fruits and vegetables. And so for there, we can say, well, what do we know if we wanted to have a robot doing that? Again, we can say, well, we know the kinematic, we can compute by manual workspace, we can generate trajectory, but what is really missing and what will remain missing is how to model a melon, zucchini, any of these vegetables. And most importantly, the fact that these vegetables change, they deform as you actually interact with them. And they really change in consistency. So for that, as my only equation, what we did to tackle that, and this is one way to approach it, is again to go back to what we know. And what we know is that typically we will have to do that with impedance control at the endpoint at least. But what we don't know is typically what will be a reference trajectory, what will be the frame of reference transform, and most importantly, how the stiffness vary and how the force at the endpoints vary. And the force change and the force pattern changes as a function of what you do because you're deforming the object. And so you can model these things and you can then show that you can transfer this knowledge to many different melons because there is no two melons that are the same, to many different zucchinis. An interesting thing is also that the pattern will change as you scoop the melon or as you peel the zucchini. So to close, as I said, I really think that the two have to work hand in hand. And my take on this is that we have to use the model when we can, because we don't want to start from tabula rasa. We don't want to reinvent the wheel. But data-driven learning, I strongly believe, is absolutely necessary because it complements the model. It's there to learn the parameters, to model nonlinear dynamics for which we don't have known models, to account for the world uncertainty. I like to put a little caveat. Sometimes I see that one uses models, but one does not verify the validity of the model. And I think it's important to do so, especially when we apply, for instance, some models that assume rigid contact and the contacts are not rigid. And so the model is really not very valid. And conversely, I think we should really not use learning when there is already a solution. We need to go further. And just to close, to me, science is really to increase our understanding of the world. So one thing I was always worried about whenever we use learning is that it was a bit of a black box. So as much as we can, we try from the data-driven learning to build a new model that we can at least say something about it. It's not always possible. I think that's the main drawback. And as we get new data, we should update the model, and we should potentially, hopefully one day, and I don't think we do that frequently enough, to change also the physics-based model, to get them informed about what we have learned. And I think we should do that at least in simulation, to update and modify our simulator that they become more close to reality. So with this, I'll stop here, and I hope I have not exceeded too much my 10 minutes. Thank you.
Thank you so much, Aude. We have time for maybe 2 short questions. I would invite both the panelists as well as our guests to direct your question to Aude.
I would ask one. Aude, thanks for the talk. I loved those examples, but in the spirit of discussion, let me push back on the first one. I feel like your statement was that we have a very hard non-convex problem. We solved it many times, we fit that to data, and then we can solve it better. No real world coming in at all. In that case, I feel like we could have understood it as just there's some regularization that you put in your GP or whatever you used that we could have understood in the initial problem. And I think in that particular case, I don't know that data is the right solution. I feel like formulating the problem could have accomplished the same.
And I like the question because it's right in your area. So it was a non-convex optimization because the constraints are nonlinear. And so the problem, as you know, with non-convex optimization is that sometimes the solver will lead infeasible solution unless you bootstrap it in the feasible space, which is not necessarily doable, especially if the robot is far from a feasible configuration. So the initial configuration is outside the feasible space. So when you run the solver, basically the solver, what is the solver doing is again searching all possible solutions, and it's consuming. I mean, it takes some time. Of course, we could run that faster. That's a separate issue. To me, the major drawback is basically that it was searching each time. It was doing the same search several times. And it's a bit absurd. If you have found a solution, then find a way to retrieve that. It will be really the same as if you travel the first time to EPFL and you come to my desk, you will probably, to my office, you will look at the map and it will take you a while. But if you do that three, 4 times, you're no longer looking at the map. You're coming straight. You have a sort of automatic solution. So that was, I think, in that sense, it's useful as a complement to current way in which optimization runs. It's a complete domain. It progresses. It could be that at some point optimization will be easier because actually we could have removed even the objective function and just look at feasibility. Yeah? That could have been an option also. But still, we will have been running the same optimization several times. So it could be that as the field evolves, then we don't need to do the data-driven approach either. But on the second aspect, when we learn the friction or the difference, the distribution of mass, I don't know. I think you're somewhat right that we don't necessarily need all the time to have learning. Because I could say that, I could say that the relative dispersion of the tactile information that I get on the fingertip should sum to 0 or close to 0, and then I have stability. And so, yes, if I knew what is close to 0, if I could model this noise, then I could put it back into my solver and then run the optimization directly on it. And I think you're right there. We should do this step. This is the step where we go from learning back to the actual optimization.
Do we have another short question? from the maybe the guests. All right.
I was muted. I mean, this is going to be a question that I probably have for everyone, which is when you decide to build in a model, I think that that's not a binary decision. Models exist all the way from incredibly detailed physics models with the mass distribution and the friction distribution and all these things, the center of pressure, up to models that are quite relaxed, right? That might give you the generic form of the controller that you want, but not make very many commitments. So I wonder what the advice is about how, if you're going to take a model-based approach, and in some sense we all have to at some level, then how do you pick the model? How do you decide an appropriate level of modeling for a problem that you have?
May I propose, Leslie, that we save this question for the final Q&A period? I think that would be a fabulous one. So we move on a little bit to hear Michael's to say and other people say as well. And then we'll come to, this is a fabulous question. I think we definitely want to talk about that. Right. Okay. So maybe that, let me invite Michael to for the second presentation then.
All right. I'll start my screen. And was really delightful to share a piece of work that is also related to robotic grasping and manipulation. In this particular problem, the issue or decision on model-based or data-based is very acute. It's something, a decision that we have to make, and we have to make it very earlier. So we were interested in building a tactile sensor that would give us quite more detailed information about the fingertip contact with an object being grasped by the robot figure. But we don't just want to have a singular tactile sensor that only indicating a resultant force. Rather, we want to have much better feeling about the contact states, about information that we care much more when we do grasp planning as well as regrasping control and manipulation. That is, we need to have force distribution information and also the state of different contact possibilities as well as potential changes. So that's what we call finger vision, where we literally put a CCD camera inside a fingertip, where the camera would watch the piece of the soft material of the fingertip under deformation during contact with object. So we hope through that measurement of deformation, we will be able to infer the contact state and also to understand the dynamics of the changes of contact. So here's a short, quick video showing you what these, what you get from this tactile sensor, if you want to call it, and then you get what we call the deformation field, deformation flow, that measures a set of pixels on the surface under the deformation, under contact with object, you get a force field, and through which we would like to be able to detect what is happening inside of contact, especially onset of slippage, or is it in sliding, translation, rotation, or other further information that you would like to have for controlling manipulation. So basically, this is essentially mechanics problem, where once you have the physical principles worked out, you build your hardware, and very much you need to deal with the mechanical properties of these elastic materials under deformation. So there are two essential problems we need to solve. First one is basically by looking at the deformation field that we are able to measure to determine the contact force distributions, as well as the force resultant. The force resultants are a good measure on the contact state, but the detailed force distribution are much more useful because that would be able to tell you more on what is going to happen and what is happening, or what are the dynamic transitions during the process of grasping. So to be able to do that, essentially you need something, either a model or based on the data you get, to be able to measure the forces in a more reliable or even to a certain point accurately. So very, very earlier, we have to face this issue. Should we use a physics-based model or mechanics-based model? More specifically, should we go with a data-driven approach? Now, for me, I'm a more classical mechanical engineer. That seems to be a very good question, but trying model-based might be more intuitive for me to begin with. But for my graduate student, Yajan Zhang, he rather used data-driven approach because it's just something that he feels cool, and he feels that he is able to learn a lot, and also quite good a show-off piece of work. So we look into that. It turns out that the model-based is possible, and there are people who build similar sensors as ours and use model-based, essentially a nonlinear finite element model. So that's classical model-based. So this is from Alberto Rodriguez group in MIT, and essentially what you have is a piece of elastic material and under large deformation, and you might be able to measure, or in our case, we already have the input, which are the displacement field, and you want to understand or be able to calculate the forces associated with each of these discrete points. And you need to use finite element. You could possibly do so as well, but you really have to be able to deal with large deformation, nonlinearity, material properties, friction, and worst, which is the boundary conditions. This is not a very well-defined structural system. It rather is fairly nonlinear and a lot of uncertainty in it. So these models traditionally be built in mechanics communities, mostly for measuring strains, stresses, but not to the point where it actually be able to show you more information about contact states, about transitions, about dynamics. So data-driven approach is also natural to come in given the complexities. And there is another group that is in ETH that uses a similar idea, but in terms of a training of a CNN network, and that approach is a little bit limited. So they use simulation under a certain set of the contact states, contact configurations, where you have an indenter and you slide over the surfaces and you're able to train to a certain degree. And then later on, you use similar setting physically to evaluate whether or not your model or your system is able to capture what is happening to the limited domain. But if you really want to go to the larger scope, where you'll be able to really say, under a variety of loading, boundary conditions, large deformations, material property, friction, I'm able to determine the force distributions accurately through data-driven. That is fairly daunting. So for us, we have not tried that yet. We take a slightly less ambitious approach where we assume that our deformation field has some major principal subfields in terms of curl, divergence, harmonic. So using the classical field theory, where you build essentially some characteristic components, and then you are able to reduce your dimensionality to a lower dimension, and then we will be able to build a network to be able to identify contact information with the reduced model. So this is what we have tried, and of course then you would need to go through training for your network and understand how successful this could be. So it turns out that in terms of those forces, sliding force, normal force, as well as torque, the estimation is very good. Also, in terms of the contact states, we can train them for different set of key contact possibilities that we care very much in grasping and manipulation. So these are translation, rotation, stable, rolling, and breaking the contact. So slippage, onset of the slippage detection is a key feature that we would like to be able to identify. So essentially, we're taking advantage of this as more like set of a video. Over time, you have a change of the deformation field, and you learn and you train, and you're able to make a good inference. So that second problem is solved using data-driven, and there are also people who use model-based. Of course, then the potential contact states and the detailed dynamic transition that you can infer is very limited. For example, you use an ellipsoid to look at to characterize contact pressure distribution to tell you where the contact is moving, but that is fairly limited. So what we have done is that using an inference network, we get to about 7 or 8 classes of contact states. We're able to pretty much detect these clusters and also classifications. So we are happy with the data-driven approach to this range of manipulation characteristics. And very much the question still remains, what if your contact situations are far more in terms of key characteristics than the 7 of 8 classes that we have organized? Can you learn to a broader level of the tasks, broader level of the physical configurations, and including materials, including texture, and perhaps even including the grasp situations, for example, multi-fingered hand grasping that cubic object, where or not these states are good enough. So my conclusion is that traditionally we use model-based, but whenever these mechanics model-based is essentially when they are not really good at it, large deformations, high nonlinearity, and the data-driven would be able to help. But similar questions, of course, remain for data-driven. So you just have to find the right set of balances in terms of whatever the best you can do, and or whatever philosophically what you like to do. And I have to say, giving my students the experience, and giving my old experience with classical mechanics model-based, the data-driven deep learning results are far more interesting and appealing and useful than what in the past I had tried to do with nonlinear finite elements modeling of viscous elastic material subsets. So for this problem, I think the physics is so complex and the models of the mechanics are so inadequate. In mechanics, people, they know this very well. The viscous elastic materials modeling is very hard. So data-driven has given us an edge, but how far can we push this to what level where we can really make this work for general robotics grasping? That still remains to be done. And also our hardware could still have a lot of improvement. For example, you can also find better materials to give you better, more predictable behavior. So that would be all I have. Thank you very much.
Thank you, Michael. Wonderful. So I think we have a question break again. And so please direct your question to both Aude and Michael from both the panelists as well as our guests. And also, we don't have too many questions on Slido yet. For all of you who are connected through the internet, please do. You can send your questions to the Slido, and I'll try to ask on your behalf.
I actually have a question. So I raised my hand on that blue thing, so I'm actually curious when so in the past I see that the developers of hardware like manipulator arms try to utilize properties that will make computation easy. So for instance, to make the Jacobian easy to compute, they set the manipulator arm in a particular way. So I'm wondering, now that we have data-driven, for instance, are there anything that can be extracted from, well, the benefit, the difficulty, or the ease of using data-driven approach to also help the hardware design? So I'm actually curious if you also did something like that in the development of your sensors.
I'm not quite sure I get your question. It's in terms of the motion of a manipulator, or in terms of the...
In both, I suppose, because I guess the thing is that now the capability of the algorithm, so basically there's the hardware side and then there's the algorithm side, right? So there are limitations that we can do in the algorithm that might actually be easier to be handled by the hardware, for instance. And last time, in terms of model-based, we sort of figure out, oh, this is easy or difficult to compute. Now that we have data-driven, are there anything that you can also bring into the design side?
So for our sensor that contact the material, as well as the ability of our optical flow tracking algorithm, is crucial to be able to at least achieve the deformation field, to be able to measure, to get the data signal. After that, to make sense out of your deformation field, to be able to compute contact forces and the contact states, contact properties, that where data-driven comes in much more handy, because the mechanics model governing the relationship between forces and the deformation, that is too highly complex in these cases. So there, the hardware helped you to be able to get sensing information, to measure the deformation flow. If you are not able to see deformation clearly, that of course the sensor will not be able to work. But once you are able to achieve the data, they're able to generate more reliable, accurate data, and figuring out the force displacement relationship, and also the contact properties. That model, fundamental model, would not really be able to do that at all. So that's where the data-driven approach that would really help. So there are two sides of it. Sensor is essential to be able to deliver the data, then deliver the information, then information processing. I would think that actually algorithm plays much more important role rather than relying on the mechanics of physics relationship that between forces and deformation, which is very hard to understand, to get.
Maybe just to agree with, I would say that it seems like our mechanical designs have been traditionally very constrained by things that we can model well. They're very rigid, they've got joints in certain places. And the dream, I think you're alluding to, would be that if we relax that assumption, can we change the way we design robots, right? And we don't have to worry about S equals MA working well for this system. And does that unleash a whole different type of mechanical design for robots? I love that idea. I think we should be exploiting it.
Yeah, I think that's a very good way to look at it, right? That's also sort of our view, because if you stay in the classical mechanics domain, you really care about strain and small strain, small stresses, very accurate correlation, constitutive equations and all of that. But that gives you very limited physical behavior. You can do a very good structure, but you cannot really get to for example, large deformation soft robots. So I think your concept where if you relax all these physical requirements, mechanics requirements that traditionally demand for structures, and now you are able to do more, far more, especially in terms of motions, in terms of the like dexterity or force closure, these type of properties.
Mark?
Yeah, if I can jump in, I think what I would love to see is our sensors and actuators that can self-calibrate and change depending on what we need, such as a force torque sensor that can suddenly change the range of forces I can perceive because, you know, we have to calibrate them. So sometimes we have to calibrate between 100 Newton. But similarly to what the brain does, suddenly if the force torque sensor could change the calibration depending on the contact force and then increase and decrease, as we see the white balancing in cameras. So it would be great to have more cleverness embedded in the sensor. And similarly for actuators, if the actuators could also change the resolution at which they can, you know, encode the difference in the joints automatically without, because that will allow us also to decrease and increase the bandwidth as needed without having to control explicitly for it.
All right, Mark, you're the next for the question.
Thanks. So I have a question to both Aude and Michael. So Aude put it the way we should use a model when we can, which I totally agree, especially when we can and it's fruitful to do. But it kind of poses the question, when can we actually use a model? And that becomes maybe the most crucial question then. And we see use cases. So Michael has some studies for this and that case, we can use the model or not. Aude, you have many use cases. For this and these cases, we can use the model and others not. And I'm wondering, is there a more principled way to understand when can we actually use a model and when is it actually useful without just doing trial and error experiments?
Yeah, thank you, Mark. I think it's a bit similar to Leslie's question. Maybe I was not clear. We always use a model. And then we complement it with data-driven method. And for us, the model are very standard kinematic, you know, just a forward inverse kinematic, forward inverse dynamics. And so, of course, they're approximation. We are aware of that. They are never perfect. And so either we use them in a first approximation. Similar, you know, I'm a physicist by training. We know that the Newton law is also a first order approximation. It holds for macro data and it doesn't hold if you go lower. So in truth, we always assume that these models that we have from robotics hold to some extent. And we account for the imprecision, which we called as noise or uncertainty. And then we use data-driven approach. I believe more and more that this is probably mistaken. We should really go back to the model and change and improve it or really question when it's valid. So I've come to the point where I question my own work.
In our case, when you really deal with mechanics, more physical system, typically it's a little bit easier to make decision whether or not the classical models that would really be able to work within the domain where your system of devices built to. Because most of these classical models do have very, very strong limitations, which are very well known. So once you get to a point, in our case, once we started to build the sensors, we know that viscous elastic on element model would be very difficult to build if it would work. So we didn't even give it a try. We just directly went to data-driven approach where we then take liberty of this particular approach, so allowing us to measure large deformations so that we'll get the full set of the distribution of the contact forces. So in the past, when we were more cautious, That's where we want our sensor to behave more predictable mechanically using classical models. Then we would restrain or select the materials much more carefully so that they would follow models more accurately. But then the performance, the motion range, all of those would be limited. So that's the classical mechanical engineer's approach. When you start building mechanical devices, you tend to think that way. You have to look at what is the task or functional requirements you are aiming at, and what are the ranges where these components, materials would work adequately, or your model would predict adequately, so that you know if you are able to achieve your tasks or range, or you will just need to focus on what you could. And so with data-driven approach, that actually opened up quite a bit of more possibilities, new dimensions, you may say. So I think for mechanical engineers, a lot of mechanical engineering students, like some of mine, even myself, getting to know data-driven approach, learn some of them, learn some of the philosophical aspects, is actually quite a mind-opening that help you to readjust how you would approach a problem and design, build it. Actually, it still would be even work better.
Thanks.
Do we have one more question? All right, I want to join Mark's question. So if I understand correctly, I think both of you, Aude and Michael, are saying that, models are good stuff. Whenever we have it, or at least we have the correct models, we want to use it as much as possible. And then if we run out of our knowledge of models, and then we'll apply data. So the operating principle becomes that we'll use model as much as possible, and then we turn to data when we can't. I wonder what's your thought on that?
Yes, but again, the reason for that is because we want to understand, we want to progress science. We don't want just to build robots for them to run. At least that's not my stake. I really want to be able, I'm a professor like you guys, so I want to be able to teach something. And in order to teach something, I need to be able to explain. And to explain, I need to be able to understand what's going on. And so to understand, I need to be able to model, and the way that we understand in our field is by writing mathematical equation, and to also interpret this mathematical equation. Because of course, from a neural network, and I've done a thesis on that, I can write equations, but sometimes I cannot interpret them anymore, neither geometrically nor with any other standard mathematical tool with stability and convergence. So I'm not too sure about what I'm observing anymore. So I'm not too sure as to what I have stored, even though I see that it does what I want. And personally, I like to go one step further. So I know it's the interpretability, but it's more than this, because it's true for Gaussian mixture model, it's true for all machine learning technique. So yes, the model, we like them. I think we're at the stage where we need to go one step further. The model we have barely changed. I came to realize that I find that science is not progressing that much. We're still using principles developed by most physicists in the last 2 centuries. So do we have principles now that we can write down from this data that we can extract and then update the models? And that's really what I want to think more about right now.
Sure. In the interest of time, let me propose that we move on to our next panelist, Sergey.
Yes, let me try to set up the screen sharing here. Let's see. Okay, there we go. And okay, so this is all set. Okay, well, maybe to start with, something that I'd like to do is to discuss a little bit some assumptions and objectives that I have in some of my work, because I think this is kind of important to frame some of the discussion that comes next. When we talk about the role of models versus data, there's kind of different ways we can approach that question, and depending on what we're setting out to achieve, I think the answer might end up being very different. So I want to, say a few words about what what I'm assuming and what I'm trying to achieve, because I think that will get things to make a little more sense. So the first assumption, which is probably not a very controversial one, is that building effective robotic systems is very hard. And the nuance that I want to emphasize here is that not all autonomous systems are actually hard to build. Like if you want, for example, an automated guidance system for a rocket or an airplane, optimal control and structure optimization methods do this very well. In fact, they actually do this better in most cases than human intuition. So you can have a rocket guidance system that's much better than a person manually trying to pilot the thing. And then when we go to a lot of the difficult robotics problems that we want to tackle today, we actually see the opposite. So if you want to fold laundry, the best optimal control structure optimization kind of system would probably do a lot worse than a person, even a person teleoperating a robot. And I think this is an important kind of fact to put up front. The second one, and this is going to get into somewhat more debatable territory, is that I think we need general solutions. Basically, I don't think we can make sufficient progress on these difficult problems if we need to develop separate methods for each task that a robot needs to do. So if we need to separately build a soup stirring controller, a laundry folding controller, a lane merging controller for a car, we're going to be at it for a very long time. And this is because open world settings are inherently multitask settings. Basically, the richness and diversity of the real world demands a richness and diversity of behaviors. And we can't afford to basically special case every single thing, because then we'll be doing that forever. So we need general methods. And the third assumption, which is a little nuanced, but I think it's important to get across, is that I think these problems are hard, not because of some issue with our methods, but because of the nature of the real world. So that is, it's not just a matter of needing a better control law, but it's actually the real world itself that's full of special cases, exceptions, and all sorts of complexity. And solving these issues is not by itself just a matter of writing down a better kind of control equation, because we can't just get rid of all the complexity and special cases. They're baked into real world environments. This is an important assumption, and I want to acknowledge that there are actually good arguments against this assumption. For example, in robotic locomotion, there's a lot of excellent work that proposes hand-designed control laws that are inherently robust to a very wide range of perturbations. So what I'm assuming is that in general, we won't be able to do this for everything, that in many settings, the wide variety of situations really does demand a wide variety of responses. And that the robot needs to really confront the real world with this large repertoire of possible behaviors. And this is a non-trivial assumption. So then I want to say what my objective is. My objective, just to kind of frame this discussion, is to address these problems so that we can efficiently and tractably build robotic systems that can reproduce a large fraction of human physical capability. So I'm not talking about like kind of the complex cognitive stuff. I'm not talking about like robotic doctors and lawyers and artists, but something closer to like robotic construction workers or taxi drivers, where they work under high-level direction from a person, but they autonomously perform physically intricate behaviors. And it's really the physically intricate part that I want to concern myself with for this discussion. So together, these assumptions on this objective suggest to me that we have to tackle the complexity of the real world. We won't find a single kind of parsimonious solution like a single control law, and we have to have a lot of exceptions and special cases. And at the same time, we want a general solution. So these things at first kind of seem incompatible, but I think they can be reconciled by appropriately using data. And that's the essence of why I think that learning-based approaches to robotics are the ones that are going to work really well, because the data will tell us about all the messy and complicated special cases. So that doesn't mean that we need robots to learn entirely from scratch. It doesn't mean that we have to do everything with deep learning. It means that we have to learn about the world from data, because that's the only way that we can handle all the exceptions and special cases and still obtain a general solution. And then starting from that, we can think about kind of what it takes to develop a research program around these kinds of assumptions and this objective. And when we think about developing a research program around this, we need to sort of zero in on the problem that we're really trying to tackle. So if the question is, can data-driven methods address the complexity and variability, we have to study data-driven methods, ideally in isolation, to disentangle them from all the other components so that we can see whether the thing is really working. So the other thing I'd like to do during this time is I want to show you a few results of settings in which data-driven and learning-enabled methods have worked well, because I do want to make the point that these approaches are actually very general, and they work very well in a wide range of settings. So when we started working on this about 6 years ago, we looked at end-to-end learning. Let me switch this so that the videos show up. We started working on end-to-end learning from images to low-level motor commands, precisely because we wanted to zero in on just what a purely data-driven method could do. And it worked decently well in some simple manipulation settings where you needed to manipulate one object in kind of a narrow setting. But since then, we've studied a number of other settings, and I think it's interesting to look at these. So one of the things we've looked at, this is a much more recent result from last year, much more physically intricate behavior. So David, in the opening remarks, mentioned the OpenAI dexterous manipulation result. Now that result actually used a simulator. So arguably that was a model-based result. It inverted a physics simulator using a very computationally intensive simulation-based approach. But this video that I'm showing here used the shadow hand robot to manipulate two objects in the hand without any simulation. This is using entirely real-world data. Basically, the only hand design controller here is the impedance controller that's trying to match the desired finger joint angles. And with about 4 hours of real-world training, you can get this robot to manipulate two objects in the palm. And if you want a new task, you just retrain it. You spend a few more hours. Generalization. Generalization is a really big deal, and generalization is one of the strong points of data-driven methods. So in this video, we tried to scale up robotic learning. We had a number of robots collecting data together, and this is exactly what you think it is. These are robots that are working together to learn to grasp objects. And one of the things that we can see in the resulting behaviors that I think is really interesting is the ability to handle those special cases and that complexity. So if you give it a rigid object, it puts the fingers on either side of the object the way you expect. If you give it a soft object, it tries to pinch it because it learned that soft objects are kind of the exception to the rule. For soft objects, you don't have to have the force closure on both sides. It's enough to just pinch the object in the middle, and that works. We've since scaled up the system using Q-learning inspired methods for sequential decision making, and it can handle very diverse objects and very dense clutter. For monocular vision-based grasping, this is probably one of the best systems you can get. But more generally, outside of this work, learning-based approaches at this point are really becoming the dominant class of approaches for robotic grasping, just because they work so well. But it's not just robotic manipulation. If we look at mobile robots, we've done a lot of work in this area, as have many other groups. You can have robots that use their own experience, basically driving around their environment, colliding with objects, and learning from that experience, both indoors and outdoors. So on the right, you can see from one of our recent papers, this is a robot that learned to navigate in kind of urban environments and is generalizing to a forest scene. And the same idea holds for legged locomotion. So this is some work where robots are actually using data collected from motion capture of real animals. This is using motion capture of dogs that they can then use to learn various agile locomotion and jumping skills. One common question that comes up in regard to learning methods is, are they efficient enough? Are they efficient enough to actually learn behaviors in the real world? And there are a lot of results that are mentioned that are kind of older results that show that reinforcement learning methods can work in complex settings, but they require very large amounts of data. It's important to note that these results are old, and things have come along a lot since then. So these are, circa 2013, 2015 results. Fast forward about, 3 years, 2018. This is Soft Actor Critic, which is a more recent reinforcement learning algorithm compared to the policy gradient methods shown on the left. It's an enormous improvement in sample efficiency. So while reinforcement learning methods do need a lot of samples, that number has come down enormously in the last 5 years. And the grasping result that I showed required 580,000 grasps to learn to grasp any object. Now that might seem like a large number, but if we compare to supervised learning results, like for example, classifying ImageNet, classifying ImageNet requires 1.5 million training samples to learn to recognize any of 1,000 classes. So it's at kind of about the same level. And if we're not happy with how well the system does, so if we do change something in the environment, so for example, maybe we trained this grasping system and now we want it to grasp some glass bottles, there's actually a very easy solution because these methods are self-supervised, so they can just keep training without any human effort and adapt to these new settings. And we experimented with this a little bit, and we found that this grasping system can adapt in about 4 hours to a wide range of conditions, different lighting conditions, glass bottles, different grippers that have been translated or perturbed in some way, typically on the order of 2 to 4 hours of adaptation time. Okay, I think I'd like to stop now because I want to make sure that we have enough time for discussion and kind of leave off on this note. Thank you very much.
Thanks a lot, Sergey. I think we'll save all the questions to the final discussion period, and we'll move on to Russ now, just in the interest of time. Russ, you're next.
Good, okay. Thanks for everybody. I took a slightly different, just like David said, I wanted to be a little bit precise in the way we talk about this today. And the question for me is sort of the deep models versus the physics models. And I want to distinguish that from, actually, I completely agree with Sergey, what he just said. I think we all agree that data is good. And I would say that even our original physicists were actually data scientists. And everybody uses data in order to calibrate physics models and even to generate the models in the first place. Our Galileo and Newton and everybody, they actually fit. The magic of what they did was that they fit very simple models to very noisy data. And maybe there's even an interesting philosophical question about whether we're being spoiled by the quality of our data these days and we don't tend to find our simple models anymore. And the other thing that's important to understand is that they didn't just give us a model, they gave us a rich class of parametric models that we, down the road, could fit to new data, right? And as just a sort of a funny thing, maybe, what if Galileo and Newton and everybody had deep learning, right? And what if what they had done was published the weights and architecture of their deep network, where would we be today? Or maybe even more scary would be if they just plotted a learning curve, that could be hard to have built off. I think, the amazing thing that they did was this rich class of very simple models. So let me try to be a little precise. David asked us to be precise here. So, a system that we're observing has a bunch of inputs. There's no start time, there's no end time. Whenever we start measuring, we get to see its inputs and outputs. We can choose to model that in a handful of different ways. Oftentimes we choose state space models, which have a state vector X, right? Which we're imbuing on the system as having some internal state. There's some noise and disturbances, and there's some parameters of the model, right? And probably you've also defined some distribution over the possible initial conditions, over the disturbances and the parameters. But that's not the only way we can choose to model. And I wonder if some of the discussions we have today about model-based versus model-free and how well do these models work are actually a little bit mixed up in this question of how people are writing down the models in the first place. So I just want to point out that there are other classical ways to write models, which disavow the idea of an explicit state. And your state is somehow the history of all inputs and sensors measurements you've read before. You can infer potentially W from what W might have been to do the prediction. And so there's no explicit notion of state there, but of course you can go back and forth between these models for any finite history. So if you think about the class of models we're talking about here, I think in the state space models we're talking about, that's where most of the Lagrangian mechanics, physics kind of models live. And it's also where the recurrent network models, LSTMs and the like, are living. They have a state representation explicitly. And then there's another class of models that have become popular lately, where we're using more feed-forward networks to predict the future of the world, where maybe Y is an image directly, and where people say the state is the image, but I think it's more clean to think about that as an autoregressive model, where you're just choosing your history of possible observations as an implicit state representation. So I think that the distinction is maybe more important in that axis. And they come in many other forms too, really, like a Q function and a value function is also a model that's is fundamentally predicting something about the future. You can choose to predict something very narrow, which is just my expected performance, or you can try to predict my outputs, which is the most general, and there are nice things to explore in between. But I really want to distinguish between model class versus model instance. Okay, so in this notation, F and G, the way I've written them down, the way I've parameterized them, describe the model class, okay? And maybe my parameter vector theta describes an instance of that model if I've calibrated it to some data, okay? And I think the question, as I heard the question posed for today, was about the model class. And really, should we prefer writing F and G using equations from physics, or should we just parameterize that in a deep network? And maybe that's just an architecture question. And I agree we can do both. And it's kind of like, to me, should we use ReLU or should we use tangent nonlinearities, or should we use LSTMs or transformers? Sprinkle in a little F equals MA, whatever. It's a representational question, okay? And it's an important one, but it's not about, well, there are different philosophical points, but let me start with that. One quick aside that I do want to clear that, I think a lot of people say differentiable physics, and we're going to do a neural model so it's differentiable. But our physics models are and have always been differentiable. You don't need neural networks, you just need the chain rule. So I just want to put that out there. So I have seen model-based, physics-based models be extremely effective for control, because you can write very strong controllers about them. This is sort of what Sergey alluded to. You can write very robust. We didn't model Andres jumping on the back of Polaris. We modeled Atlas and asked it to be robust to uncertainty about its perturbations, and it was very robust, okay? And then the cool thing, in the spirit of generalization, was when NASA sent us a robot, about 3 hours after we got the robot turned on, we had it walking with the same controller, and Lucas was again pushing it with a 6-foot pole. So the generalization power of the model-based approaches, or the physics model-based approaches, are potentially very good. But there are other problems that I'm thinking about that just break my model-based view of the world. And I want to just it's a subtle point for why. So if I think about writing down the model and doing the state estimation for this and doing a planning control for this, and if I think about the state of the mechanics as being every piece of the onion and it's changing every time the cut happens, then my brain starts melting. So here's a place where the physics, I think, feels like it falls short. So I agree with what Aude said, that all models are wrong, some are useful, but let's quickly say what makes a model useful. And I think what makes a model useful depends a lot on the use case. And so I picked two. The first one would be like a simulation use case. For instance, if we're gonna generate synthetic training data to train a control policy or a vision system, for instance, or if we want to do Monte Carlo testing to just, we already have a controller, we want to understand how robust it is, or if we just want to use it in a design loop to do model-based development, right? So if that's your use case, then what makes a model useful might have a different answer, right? So first of all, you'd like it to be reasonable. You'd like that the predictions that come out of your model to be things that could actually happen in the real world. You'd like it to have some sense of coverage, right? You'd like that for all things that the real world could happen in the real world, you'd like it to be possible for your simulator to generate those solutions. And ideally, you'd like it to be accurate, although whether you need this is an interesting question, but ideally, even the distribution of outputs that you'd make by your simulator is somehow calibrated as close to what the distribution you get in the real world. So as a corollary for this, I think we want reliable system identification. We want to take our data and figure out the parameters of our model. And you could argue that for some really hard problems, maybe deep learning is doing that better than our model-based things, although there's some classic results in model-based and sort of equations of motion for robotic manipulator system identification that are extremely strong and much stronger than we would get from a deep model. Of course, you want generalizability, efficiency, repeatability, interpretability, debuggability. I figured everybody would cover this before. I think they're maybe lower on the list for just simulation. And boy, I would not bet against whether we can simulate things. This is a simulation that I love of baking, right? It's a material point method. Anything you see in the kitchen, I think we could simulate. So I wouldn't bet against the power of physics-based simulation. The Unreal Engine trailer is another great example if you haven't watched it. But there's a very different use case, which is online decision-making for planning and for control. So what makes a model useful for that? So I think you'd want it to be reasonable and accurate and generalizable, but maybe there's an additional burden that you could somehow be efficient or compact, right? And you'd like it to be something that you can think about and make a decision about. And there's a really important one, which is that it's somehow observable and probably that it's task relevant. And let me zoom in on that a little bit, right? So the state space versus autoregressive. Like, do I learn a model from image and action to next image, for instance? The nice thing about that is it doesn't require state estimation. You're using an implicit notion of state from your recent observations. And the pain point of having like a Lagrangian state of my onion is that I don't want to do state estimation of all the pieces of the onion, right? So if I'm chopping onions, it's not just that it's a complicated model, but it's not an observable model. The burden of trying to estimate the state of that system in a Lagrangian sense is too much. And you don't need to estimate that state to accomplish the task. Okay, so I think this is a super important point, whether it's deep or physics. It doesn't imply, though, that you should throw away mechanics. You know, there are different state representations you can do that can start from mechanics. And maybe I think, you know, the biggest philosophical difference, I would say, between the deep representations versus the mechanics representations is something about Occam's razor, and not just predicting what will happen, but really what won't happen. And, you know, in physics-based models, F and G are not arbitrary. You know, someone went out on a limb and they said, not only, I mean, that's very rich, but it's not universal, right? There are some things that will never happen in a physics-based model because there's constraints. There's conservation of mass, there's conservation of energy, there's maximum dissipation. There's some things where people went out on a limb and said, I don't think a model will ever generate this. And arguably, those are the constraints that give our models the structure that we need, I think, to make better decision-making algorithms, right? That's why things are control affine. This is why the inertial matrix is positive definite. This is why inverse dynamics have branch-induced sparsity. It says something about if I, you know, wiggle my finger on my right hand, it doesn't have an immediate connection to the dynamics of my left hand, except for the, you know, through the forward dynamics can couple it. Okay, and arguably without structure, we might be really, you know, tying our hands on what models, what design approaches we can ever take. If you never tell me anything that my system can't do, then I somehow random search and gradient methods are basically the best I can ever do. And it gives up on the dream of doing more structured design. So my summary here is, I think, you know, for onions, laundry, peanut butter, all these good examples of things in the kitchen, right? I think the failing of our physics-based models are mostly not their representational power, but the unreasonable burden of estimating the Lagrangian state and parameters, arguably, on the fly, okay? But I also think that deep models are failing in those cases, because right now I could learn a deep model of that from image to image. And I think we have an inability so far to do efficient, reliable planning online, you know, control design and analysis. So like Aude, I think, you know, I want the next Newton to come around, and I would ask him or her to work on onions, laundry, and peanut butter. So, okay, I'll stop there.
Thank you, Russ. So I think now we open up for questions. I think I'll start by fire off a few questions from the net. There are a few questions that are related to this. They mentioned about repeatability of data-driven models. They mentioned about mission-critical systems. So I think the one natural question here is about the robustness of data-driven models. How do we make data-driven models robust? And more importantly, for mission-critical systems, how do we guarantee the robustness or safety of such systems? Maybe our panelists want to take up this one?
I could start. So I think if you have a mission-critical system that needs to do perception, the most robust method is a data-driven method, because there's no other choice. You can't do perception without data. So, you know, for that reason, it's like, but maybe the less facetious answer is, the reason that robustness is an issue for learning-based systems is because learning-based systems are tackling a harder problem. So if you're doing perception, perception is a harder problem than convex trajectory optimization. So robustness will be harder, because the real world, the thing that you're actually perceiving, is going to throw lots of curveballs at you. Now, it's a real serious challenge. It's a major research question. But I think it's a big mistake to pose the question as, how do we fix this problem that learning systems have, which other systems don't have? Because that's not the question. There's no other system that can handle real world perception other than a learning-based system. The question is, how do we have robust systems that deal with complex and unpredictable real world settings? And that's a challenge for any system. Now, in terms of how we can do it, I think good, sound statistical methods are the techniques that are going to get us there. And we do have good tools about reasoning about uncertainty, about reasoning about epistemic uncertainty even. They're not good enough, they're not perfect, but they're kind of on that right path. And you know, every year we see better and better techniques for things like epistemic uncertainty estimation, including with deep nets. And that's probably the way to go right now.
I'm happy to add to that. So first of all, I welcome the question. There are two aspects in that question. The first one is repeatability. To have repeatability, you need to have the same condition to start with. In the real world, you rarely have that. So I take the example of the melon scooping. No two melons are the same. So what is interesting is to show that what you have learned sort of generalize, or at least can do the same thing for various melon or various onions, etc. But for the same condition, you would like at least to have the exact same output. In all the model that we develop, the system is deterministic. So same condition will lead to the same outcome. We often care also very much about being able to say something about what's been learned. So when we learn, I did not talk too much about it, but when we learn dynamical system, for instance, we know we have guarantee of stability. When we learn impedance, variable impedance models, we also have guarantee on the energy of the system that will not exceed some energy, and we will have passivity. So these are somehow guarantees for the model itself. And I think these are important questions.
Great.
Maybe if you, well, I would love to fight back a bit on Sergey if nobody else does, because it feels like somebody should.
Please, Mike.
Okay, cool. So Sergey, I loved your first slide, which had these assumptions. That was really cool. I loved it. And the third assumption was talking about the inherent complexity of the world. And that's super interesting. I totally agree, you know, on that. It seemed to me though that your twist was that from that you concluded, because there's so many exceptions in inherent complexity of the world, the only solution is learning. And there is like two things going through my head. First thing, models, many models actually lead also to a lot of complexity. So that complexity, especially the combinatorial complexity, can very well also describe by models. And the second thought that I had is, but exactly if there is such a combinatorial complexity in the world, learning would require a combinatorial number of data in order to get all these exceptions and so forth and so forth. And in that view, why would learning give you robustness?
Yeah, that's a good question. I don't think that the existence of combinatorial complexity in the world implies combinatorial explosion in training data requirements. And the evidence we've seen, certainly, for example, in computer vision, indicates that that's simply not the case. And the explanation is that learned models do have compositionality. They have compositional inherent, they have learned compositionality. And the evidence for that is that you can train, for example, an object detector or an object classifier with data requirements that don't blow up exponentially, certainly not exponentially in the dimensionality of the image, but not even exponentially in the number of classes that you're classifying. Yes, the combinatorial structure is present in the world, but it does not appear to lead to an exponential explosion in data requirements.
Yeah, I agree if the learner is Newton. Sorry.
I just want to stick my oar in, and then we should recognize some of the students who have their hands up. My oar in that water is that we get compositionality even in vision systems because it's designed into the structure of the convolutional network. So that we can build, I mean, this is always sounds like more of a fight to me than it needs to be in some ways, right? So if you need compositionality in the models that you're learning, you can set things up so that you learn models that are compositional. ConvNets are compositional in a way, graph neural networks are compositional in a way, learning planning rules is another kind of compositional thing. So I think we just have to figure out what properties our models need and then try to set ourselves up so that we can train those. And then there will be some amount of argument about whether humans have enough insight into their problems that they're trying to solve, that they can set the structure up right. But that's a more complicated question. But let's let students ask questions.
All right, great. Do we have questions from any of our guests?
Yes, I do have a question. It's about the theoretic guarantee thing that we used to have in model-based approaches. So in classical model-based approaches, of course, on the classical assumption that we have perfect or models with bounded error, we can often provide very strong theoretical guarantees, for example, completeness, optimality, bounded risk, and so on. But apparently in the real world, this assumption is broken, and we have to rely on approximate models. So the question is, do you think the classical theoretical guarantees are still valuable in the real world robotics? And do you think after we bring in data-driven approaches, do they break these guarantees, or do they reform these guarantees? That's my question.
I would argue that the guarantees were also always in our heads a little bit, that even I think the most serious robust control person would admit that their model wasn't right. And really what's happening when you make a model and you put some uncertainty bounds and you say, be robust to this and prove something with optimal, really what you're doing is you're sort of regularizing your solution to be robust to that kind of thing. And if your uncertainty model is like close enough, then being uncertain to a bunch of stuff, or being robust against a bunch of stuff makes you sort of work in the real world. But I mean, maybe the deeper question there, or the related question there is just that, like, why do we get on an airplane? Why do I get on an airplane? Well, not this month, but why did I used to get on airplanes? I mean, it's kind of crazy because every one of those was certified with a relatively questionable certification procedure, and then the fact that the whole thing was sort of certified in parts, and but it works mostly. The airplanes don't fall out of the sky. Somehow the question is how do we convey our certificates of robustness, our confidence about the performance of the system to a human? It's probably not a Lyapunov function. I wish it was, but it's probably not that. So there's something about maybe the social contract there that we've got to figure out.
Okay, so there's a question from Yonghyun.
Yeah, I have a question. I think Professor Aude and Russ commented on this topic in the presentation. It was, for me, it was so exciting could we find a new physics-based parametric model, or per se physically interpretable model over the Newton's law? I mean, my question is, would it be possible, and should we go forward to find a new physically interpretable model? And more question is that, would neural network be the candidate? That is my question. Yeah, that's all. To Professor Ross and Aude.
If you want to go first, you should go.
Okay, so answer is yes, we should, we must, we absolutely should do that. At least I definitely would like to. And I mean, maybe we can wait for another Newton to come, or maybe we should all work to become one somehow. But by the way, I think there was a fundamental difference between Newton and all these other people and us, is that they were not working for science. They were doing that as a hobby. And they looked at the data because they cared about understanding the data and not about using them to generate a new system. Actually, other physicists such as Maxwell or even Marie Curie had an engineering brain towards how to use the data, but it wasn't the case for Newton and the other people you mentioned. So yes, I think we should do that, especially for the deformable object. What can we say about that? What are the rules of motion? Maybe they're simplistic, but at least just getting a sense of what we call the haptic pattern of communication. I've heard that very often. What does that really mean? I mean, when I'm interacting with something that deforms, like a door, what is happening there? Can I quickly model that as a very simple equation, the deformation, the spread of it, with some nonlinear function? Probably. Will the neural network be a solution? I mean, you can look at the equation in the end. But the problem is that you have so many of them, so it becomes fairly tedious. Frankly, it would be as if, I'm sure, I mean, if you were one of my students and you go on the board and you have a number of equations, and I ask you, okay, so now please draw, you know, a geometrical interpretation of all these equations. You're incapable of doing that because we can draw 2D or 3D. But that doesn't mean that we should not try having some level of understanding. It's been mentioned before. The key idea of Newton, or the key idea of even Einstein, the thing that we've retained is what? A simple concept, conservation of energy. In fact, it's the interpretation of the equation that we usually conserve, because if you look at some of the equations that these people have developed, they're fairly complex. They're very, very difficult to understand. I mean, just the expansion of the universe. It is not just a single line. It's much more complex than that. So there is some level of also interpretation. It could be that we can have a neural network which is super complex, and I don't mind, as long as we're capable of saying something about what is the fundamental principle that it extracted. And at this stage, I feel sad, really sad, because I'm not too sure I can have much of an interpretation of what we have done in my lab. We're working hard on trying to express this, and I think we will have some level of modeling coming out in a book that we're preparing, but still, I'm not too happy. So I'll be curious to hear what Russ has to say about that.
I thought that was an awesome answer. I don't have so much to add, but optimism. I will add my optimism. I think that you know, time and again, for these very complicated, you know, manipulating laundry, opening doors, whatever, I've seen clever roboticists write very simple controllers. I've seen babies, you know, do impressive things. I have to believe that. So if you're trying to model, you know, predict the exact geometry of the laundry when you start folding, maybe we'll never have a simple model of that. But if you want a model that's enough to get the task done, I believe that there are very simple models that go a really long way, and we haven't spent enough time finding them yet.
Wonderful. I think we are almost about to end, but I want to end by going back to Leslie's question. So Leslie's question is, maybe I'll rephrase a little bit. So suppose you want to use data-driven approach, then do you want to model, and what do you model? Now, if you want to start with models, then what would you use data for? And I want to ground these questions in the since we all like kitchen, so we all in the I think both Aude and Russ showed the videos of kitchens. So let's say that we want a teacher get a robot to go to the kitchen to peel the skin of a bunch of different fruits. And we also want it to use a knife to cut a bunch of different vegetables. And it is possible that while I'm cutting that, my knife gets chipped, and maybe I need to sharpen the knife. That is what we want our robots to do. Then can I go around all the panelists, and I invite you to comment on what would you model and what would you use data for? Whom would like to go first?
I volunteer, Sergey.
Okay.
It's what you described as a very difficult engineering problem. So I don't know if I can come up with sort of the engineering blueprint on the spot, but maybe one more vague or more general thing I could say is, I think it's important to remember not just the value that we get out of having the right model, but also the value that we get out of generality. And maybe it's easier to illustrate this with an example. You know, let's say that you have some electronics device. Maybe that electronics device has some circuitry in it. These days, a lot of embedded devices that we use, they actually have a computer inside of them, even though they don't need it. So most things that you would need an embedded device for, you can just design your custom built integrated circuit, and it would do the job more efficiently, more power efficiently. It would be more minimalistic. But nonetheless, usually when you build a device, you just stick some cheap little ARM processor in there. Why do we do that? Well, because it's just way easier to engineer. So generality has a lot of value, like monetary value, power efficiency value, etc., just because we don't have to redo all the engineering. So while it's true that specific, domain-specific abstractions that humans come up with, that roboticists come up with, can be very clever, very efficient, and very useful, there's tremendous value in that generality. And I think when we actually go to build systems that work in the real world, like the one that you described, the people that actually go and build those systems, who are going to be engineers and not scientists, will probably opt for the simpler general solution when it's available to them, because it will just save them time and money. So that's kind of the slightly long-winded way of saying, actually, data-driven and learning-based solutions are likely to be effective and adopted, even in settings where there are clever models and abstractions that we could build. Never mind the settings where we don't even know how to build them. But the short answer is I don't know how to build that onion peeling or this fruit peeling robot. That sounds really hard.
Who's gonna go next?
I can go. So, okay, if I take on that problem straight up right away, I go to Michael Sherman and his team at TRI and ask him to start a simulator project, because I know he can simulate things like that. Whether you could ever take a particular zucchini in the lab and simulate exactly that zucchini, probably not, won't try. But I think simulating things kind of like zucchinis would be enough that we can practice in simulation and get get our head around the problem. At the same time, right from day one, I start running the robot, doing simple experiments, and start collecting a lot of data, and start asking the question, how well does those simulation models match the data? Can we calibrate? Do we need to augment them with less parametric or more deep type models? All great. But for the engineering practicality of it, what I really want is a model that I can run repeatable experiments on, and bang on it, bang on it, bang it on it with my control design and my verification algorithms. And the simpler the model, the better.
Michael, do you want to go next?
Let me just add that I like what Sergey has said. I think for models, they really work very specifically, and most of them don't really generalize broadly. I can think of very good models can do metal cutting. I can cut very precise piece of metal with a small, precise chips, give you right precision and right surface finish. But there's no model can predict chopping or peeling of a squash and peeling of orange skin. Even you peel the potato skin. And physics models are not built for that, because there's no generality. It has to be really well defined within those basic laws that you specifically apply for specific situations with a lot of requirements and assumptions. So generality, that's very essential. I think that's where data-driven approach really comes in useful and essential as well.
Maybe Aude, and then I saw that Leslie wanted to maybe answer her own question in the end. No, okay. Now we have Aude to give the final remark.
Actually, I will hand it out in a second to Leslie and Mark, because David, in your question, I heard that there was a twist. Maybe I misunderstood. The robot breaks the knife at the end, right? So the issue is then, what does the robot do with a broken knife? And that's the key difficulty, is that then the robot will have to find an alternative to the knife. So if the robot is rigid, it could reason and think that it's rigid enough to be able to cut. But in order to reason, then we go back to the question of how can it reason? How can it know that this new part of its own body can be used in terms of a knife? And that's not my area, but I hope that Leslie and Mark, who are doing planning and reasoning, can solve that for us.
Well, okay, I'll say something then, maybe, which is, I think a critical thing to be able to handle something like that is, right, it's fine to have compiled policies and tight models that are efficient and good in the moment, but critically, they have to be sufficiently self-aware in some sense to know that they're not applying anymore, right? That the predictions aren't working out, things aren't okay in a sense. And then we really do in some ways get to, I guess, the question that I was asking, which is that I could imagine a robot having a stack of models at a variety of different levels of fidelity and slowness probably, and maybe, but then maybe we have to shift to a different model. Like maybe it's like pretty good at chopping onions and it's just got a reasonably compiled onion chopping thing, but it starts to not work well. And then maybe it has to fall back to some kind of much more first principles kind of physics model that says, well, if my knife isn't working, it must be because it doesn't have the good knife-like properties anymore. And maybe I could restore them, or maybe I could find another tool. But I think a multiplicity of models is probably what you need to get both efficiency and kind of robustness and generic reasoning.
Okay, so I think that we are running out of time. I just want to show one last slide as a way of ending. Can you see my screen? I'm not sure we have actually reached a conclusion. I hope that we make one step for model-based and data-driven approaches to move towards each other. I think both are needed for the future of robotics. So I want to thank again all the panelists, all the guests, and all the friends and colleagues connected through the internet. Thank you. That's the end.
Thank you, David.
Thank you.
Thank you.
Goodbye.
Thank you, everyone.
Thank you.